3-6 projectile motion, part 1, I believe. I think I'm gonna have to make 2 videos on this. And so for now, you'll work just number 1 and 2 on the worksheet. Okay, so projectile motion. Now, what projectile means in physics, any time that you, like say, how would you say it? Throw something or launch something into the air, how is its motion going to be affected by gravity as it travels? That is what projectile motion is. So, like for example, if you throw a ball, throw a baseball, okay, or a lot of times, or of course, launch a rocket, or how about on a football field, you kick off a football. That'll be the problem I'll do later on. But you kick the football, it goes up, it comes back down. How would you describe the motion and make predictions? How far will it go? How high will it go? How long will it take to hit the ground? That's the kind of stuff we'll be doing right here. So this becomes very useful. Okay. Now, this is there's 2 kinds of problems we'll look at. And anyway, first under 3-6 in the notes, I'll read off, it talks about projectile motion, the motion of any object that projected into the air and then accelerated downward by gravity. Okay. So it can be true on Earth or anywhere else on the moon. Of course, you'd have to use the gravity for the moon or gravity for Mars or gravity for any other planet if you weren't on Earth. It says, in projectile motion, objects has 2 velocities. We think about the horizontal velocity and we think about the vertical velocity. So the Vx will be horizontal. You've seen that before. And Vy will be the vertical. And so we are going to be looking at a little bit with angles on this lesson. It comes in. It says there's no acceleration. We assume there's no acceleration in the horizontal direction. That's an interesting thing. When you throw a ball or an object, whatever, to someone else straight horizontally, just say you playing catch with a ball, or with a basketball even, you throw it that way and then back and forth, back and forth. We assume that when it leaves your hand, if it's going at 2 miles per hour when it leaves your hand, when it hits the other person's hand, it's also going at 2 miles per hour. So, in other words, it does not slow down in the air at all. Now, if you were up high on a building and you threw it to somebody down below, well then, yeah, gravity is going to cause the vertical velocity to get higher and higher, going to go up. But horizontally, nothing changes the velocity. Now, in real life, air resistance can actually do that. You know, air can slow down something. Air resistance is like friction against the air, pushing against you. Okay, but we assume there's no air resistance. We will ignore that because we can't ignore it. For a lot of objects, it doesn't matter. Like throwing a real heavy or dense object, like a rock or something like that, or a cannonball, whatever, a bowling ball when you're bowling. Air is going to have very little effect to slow down a bowling ball, okay, or a rock. Now, for a beach ball, it will be different, and we're not going to be using those. Okay. Number 2, we assume there's constant acceleration because of gravity in the vertical direction. And so we already talked about that in the last lesson. So in the vertical direction, it's doing a free fall. Now, let me just begin with letter A right here. And it says, a ball is kicked horizontally from a roof at 8.71 meter per second, and it lands 26.4 meters from the base of the building. Calculate the time of travel, and B, the height of the building. I have a worksheet that is like a pre-lesson to this. I'm probably going to give it to you, but you might be watching this right now. I'm probably going to say, watch a little bit of this lesson and try this, and then the next day you can try to do the math part. So I'm probably going to do that because it's a good lesson that kind of outlines everything on it. But let me draw a little picture here. So here you've got a building. We'll just say you're on top of a building. All right. Now it says that a ball is kicked. So we'll put our little friend Lily here, and here she is. And I guess she could be that way, can't she? Yeah, her foot could be like that. She'll stand on that foot, hopefully not fall down. Have her arms up, whatever, and give her some hair. And so she kicked the ball. she kicked the ball to roll off the side. So what we're saying is it's kicked horizontally. Now, if she kicks it up at an angle, that becomes a little bit more difficult problem that we'll see in the next part 2 lesson. For now, she just kicks the ball straight ahead like that. Now, we know that if the ball is going straight ahead at 8.71 meter per second, I'm going to draw a little arrow, like a vector. That is the velocity it starts rolling at. Now, if this were a straight road, flat, completely flat road, then we will assume that it will go 8.71 the whole way straight on. Now, but it doesn't do that because it's coming off the building, it's going to fall down. So we know it's going to come down like that and then hit the ground somewhere here. So that's what's going to happen when she kicks the ball off the side. So the question is calculate the time of travel and calculate the height of the building. So I'll start off with time of travel and the height of the building. You know, one thing, oh no, it did, one more bit of information they gave you. It lands 26.4 meters from the base of the building. So it lands 26.4 meters. That means the base, the bottom. From here all the way to where it lands. Let's make the ball a little bit more bally. Let's make it a little red ball, and we'll put it right there too. So there's the ball. So there it was, you know, boom, 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 and there it is. Okay. All right. So we know how far it went from the building. Now, that is called the range, R-A-N-G-E, and it's delta X, like the displacement. That's the horizontal distance that it went. And we also had up here the initial velocity. That was the initial horizontal velocity. So I can put VO, and I'll put a little X there, meaning the initial horizontal velocity is 8.71. The range, the delta X, is 26.4. Now, there's also another velocity, which you don't see right here, but you'll remember from the other day, and that you have initial Y velocity is 0. Even though it's moving in this direction, when it starts off, it is not moving at all. Vertically, it is not moving. And so it's going to just fall straight down vertically. Now, the initial Y is 0. That will be true unless you threw the ball down like that, or if you went and you threw it up in the air, and then it came back down all the way. If she kicked it up, or if she kicked, or she wouldn't really kick it down, but maybe she would bat it down with her hand, then the initial velocity Y would not be 0, but we have to figure that out. But anyway, initial is 0. We also know that in the Y direction, the acceleration, if we'll call it the Y, is negative 9.81. Okay? And then we know, let's just see, we know this distance is here as well. Okay, so it looks like we don't have enough information yet, you would think, but there is one more little bit, there's one more thing we can find out here, and I'll show you that in a second. Okay, all right. First thing, I told you about Vox Vat. You remember how that works out. And you can do like a Vox Vat for this, Voy Vat, if you want to call it that. V-O-Y, V-O delta Y, V-A-T, and that's gravity. Okay? That's not going to help me right now. I need to get one more bit of information. Like I have the initial velocity, I have the acceleration, okay? But I don't have the final, I don't know delta Y, that's the height of the building. Delta Y will be the vertical height of the building. And I don't know the final velocity when it strikes the ground. I don't know what the final Y velocity is. But there's something interesting about this. So here I have a vertical problem, and I also have a horizontal problem, Vox Vat. Now in this direction, I have the initial velocity. And I also have delta X, the distance. So again, I don't have the acceleration, and I don't really have the time. But there is something interesting. We assume that the initial is equal to the final velocity. So we actually have the final velocity and the initial velocity. The initial and the final are the same, 8.71, because we assume that there's no acceleration. It's constant. So you start at 8.71 horizontally, and down here the horizontal velocity is still going to be 8.71 when it lands. But here's another truth I can tell you. What did I put at the beginning of 3.6? Number one, there is no acceleration in the horizontal. And I wrote a little equation there. I didn't mention it earlier. And it says this. In the x direction, your average x velocity is equal to your initial x velocity, and it's equal to your final x velocity. Because remember, there's an equation that looks like this we hardly ever use. That v initial plus v final divided by 2 is your average velocity when you have constant acceleration. So when there's no acceleration, I'm sorry. That is true. But when you have zero acceleration, well, maybe it didn't have to be constant acceleration for this one. Your average velocity will be your initial plus your final over 2. Because 8.71 plus 8.71, you double it, divide by 2 is 8.71. I'm just trying to show you this equals this equals this. And so your other equation, delta x over t, is your average velocity. So that's going to be an equation that we can use to start off with. So, what I wanted to tell you on 3.6, we gave you two things. Number one, no acceleration horizontally. Number two, there is acceleration, 9.81 in the vertical. And there's a third thing that I could put on there, and that is for both the horizontal, horizontal travel and for the vertical travel, the time is equal. Aha. So, anyway, we'll go back to this. The first thing I'm going to do is I'm going to say, all right, this is an equation you always want to look at when you're doing projectile motion. Do you know the? Let's put an input at x there, because it's really going to be true in the x direction, but it can be true for y if you wanted. But all right, Vx will be delta x over t, or average Vy equals delta y over t. I don't think you're really going to see this come up very much at all. I don't think I'm going to give you any problems like that. Maybe you're in your book when it could be something like that, but I don't think you're going to see this exact equation, but that one you'll see a lot on projectile motion. Okay, but that one will be true. All right, so in the horizontal direction, 8.71. Remember, Vox, the initial x velocity is equal to the final x velocity, which is equal to the average x. They're all the same. So that is also 8.71. So I'm starting to do the math here. Equals delta x. We know delta x is 26.4 divided by the time. So look at that. We can find the time of travel. So 8.71 t. Sometimes I like to curve the t a little bit. Equals 26.4. Divide both of them by 8.71. And I get 3.03 is my time. That'll be seconds. So what this tells me is this ball traveled straight ahead this far. And it stopped there. Well, it hit the ground there. That's when it fell down. We're going to ignore the vertical for a moment. It just went this way, right there. It went 26.4 meters, and that was its speed. So it took 3.03 seconds to do it. Now, it took 3.03 seconds for the ball to travel horizontally that far. Well, also, it took 3.03 seconds for the ball to hit the ground. We know that. So they both came together. So we know in the vertical problem, we got this. Now, in the vertical direction, we got our initial was 0. Our acceleration, negative 9.81. And now we know the time is 3.03 seconds to fall straight down. So let me take that 3.03. That was your time of travel. Now, today, this is the only kind of problem we're going to do in this first assignment. And tomorrow, we'll look at the next lesson, whatever that's going to be. So if something went up and came back down again, then you'd have to double the time that you get. But that didn't happen here. It only went down. Okay, so you might remember in free fall we did that thing where we went up and down. Well, we're going to see that later on. Oh, I didn't want to erase my picture yet. Okay, let's put the little ball back. Okay, so, the ball got larger. Okay, here we go. All right, there it is. Now, okay, so it takes 3.03 seconds. So we can now find out. Now we can find out the height of the building, delta y, and we can also find out what was the final y velocity. They didn't really ask for that question, but we could find it out if we wanted to, though. But let's just find out the height. Can we do that already? The initial acceleration time. Yes, we can use the equation delta x. Yeah, this is the one that we use for free fall motion. This can be done two ways, but I will go on and use this. You know, well, I tell you what. You can use this equation. Remember this one that says delta x equals VOT plus 1/2 AT squared. All right, you could use this to change it to delta y. Delta y will be VOT plus 1/2. It'll be in the y direction. 0 would go in for initial velocity here. That's easy to do. Plus 1/2. And of course, that's negative 9.81. And then you put 3.03 squared. Well, I guess I'm already doing it. I was going to say maybe I ought not do it, but I guess I am doing it here. 3.03 squared. So I kind of wrote it low. 0, 1/2, negative 9.81, 3.03 squared. 3.03 squared is 9.18. 9.18 times negative 9.81. And then times 1/2. So 9.18, 9.81 divided by 2, 45 is the answer. 45.0. It's negative 45.0 meters. Now, does that show up? Yeah. Negative 45.0 is delta y. Because your y, remember you changed, your change of position was 45 down. That means that the building was 45 meters high. Okay. The time of travel and the height of the building. Oh, okay. We got time of travel, 3.03 seconds. B, the height of the building. So that would be B. I guess I could have left my time up there. Let me just show you, if you wanted to, you could also find the velocity that it had when it hit the ground. Now, on the homework, one problem is just like this. But then the next problem is a little bit different. Like I think I gave you the time of travel, but I didn't tell you how far it went. Or maybe I didn't tell you the height, or I'm not sure. We'll have to look at it. So I want you to try that. I want you to do number 1 and try your best to do number 2 as well. But let me just go and show you, though it wasn't asked, what is the final y velocity? We know the final x velocity is still 8.71. But the ball that started at 0 in the vertical and came down, it's getting faster and faster when it hits the ground, boom, and it's right there. What is that? So I would use this equation. The final, well, I could also use, well, no. I was going to use that one. You can use that, v final squared, v initial squared, but I can be even easier than that. Remember, if you're able, always use this equation. Acceleration is v final minus v initial over time. That's the easiest equation. You always want to have that right there in front of you. Okay, so negative 9.81 equals v final, we don't know, minus 0 is your initial, and the time was 3.03 seconds. And 3.03 times 9.81 is 29.7 is equal to v final. Now it's negative, but that's because it's going down, because remember, acceleration is negative and the velocity final, v final for the y would be negative 29.7. Okay, let me think, is there anything else we could find? We can find that. We can find the final. We already found that. We found the final velocity. We for the horizontal, we know the initial and the final are the same, 8.71. We know delta x is the range. There is acceleration is 0. There is no acceleration for this when it went constant, 8.71, and the time is 3.03 seconds. So yeah, we found everything you could find on that problem. All right, so try to do, for sure, letter A. You should be able to do the first problem on the homework. A, number 1, A and B. That should be easy because it's a lot like the one I just did here. But then on number 2, it's a slight variation, and it will say something like, I guess I could look it up and see. It's going to say, oh no, I don't have it in front of me now. Well, do I want to look at that for you to kind of help you set it up? Let me see. Yeah, okay. It says, I'm looking at the problem now. He jumped off this high and landed at that speed. He ran horizontally into the lake. How far did he land? And how long did it take to hit the ground? Okay, all I'll tell you is this. On number 2, the first thing I would do would be to do number 2B, then go back and do A. Because 2B says, how long did it take to hit the water's surface below? When you do the homework, number 2, do B first. And remember, again, on this problem, he's going to run horizontally off and jump and go into the water. He's not going to jump. He's not going to dive. He's not going to jump up. He's going to run straight ahead off the side of the cliff or whatever and then land in the water below. So when he does that, his initial y velocity is going to be 0 again, and its acceleration is going to be 9.81. That means you can figure out how long it takes for him to get to the bottom, because they gave you the height of the building in this case. They did give you the height. So if I know the height of the building, so I'm just telling you, if you're looking back at this later, like for the homework number 2B, you're going to know for the number 2B, you know the initial velocity is 0 in the y direction. You know delta y, and you also know the acceleration is negative 9.81. That means you can find the final velocity when he hits the ground, which doesn't really matter. You can find the time, and it'll be easy to find that using one of those equations. I would try to use the acceleration equation. Well, you can't use that one because you're not going to know the final velocity. Well, let me think about that for a minute. Well, go through all the equations I showed you to see. One of them, there's 2 of them that I think you can use. So okay, that's all. And I'll do a part 2 and show you the next problem next time.